Let's get done with this. We're finishing the waves packet problems. Array of monochromatic light, and we get a frequency. Oh, I recognize that number. Reference table, page 2. Here we come. In air is incident at an angle of 30 degrees with corn oil. So we've got, comes in. Let's draw the normal. Boom, boom, boom. This is air. This is corn oil. That's a 30-degree angle. And it says, what is the angle of refraction? We want that. So n equals 1 for air. And let's look up corn oil. Here we go. That number, frequency right there, 5.09 times 10 to the 14th. 5.09 times 10 to the 14th. Same number. Corn oil, 1.47. So then let's do this. 1 sine 30 equals 1.47 sine theta. So theta is going to be the inverse sine of sine 30 over 1.47. There's not really enough room here. I'm just going to write on this. So if
attention please,
sine theta is going to be
response committee is meeting in the main office conference room at
oh my
this
gosh.
time. Not in the library, in the main
Sine
office
30 is a half.
conference room. Thank you.
Ignore the announcement. Divided by 1.47. So the sine of theta is 0.34. So theta is the inverse sine of 0.34. Second function, inverse sine of that same answer. And I get 19.9 degrees. It's probably going to round up to 20. 20 degrees. Okay, the speed of light, frequency again, in a transparent material is 0.75 times its speed of light in air. The absolute index of refraction of the material is approximately, well, they gave me that number, but I don't think they needed to. Let's see, N equals C over V. N equals C over V. So if C is the speed of light, and V is the velocity of the material in that material, and it says that it is 0.75 times C, speed in air, but we're going to say air, and the speed in air is pretty much the same as the speed in a vacuum, because they both are 1.00, so then you get C, so N is basically 1 over 0.75, the inverse of 0.75, so 1 divided by 0.75 gets us 4/3, 1.33. So let's round it to 1.3. Okay. We got air, lucite, medium X, and air. Light travels slowest in, well, it's going to be the highest index of refraction, not going to be air. Lucite is 1.5. Medium 1. Let's see. Now, medium Y doesn't tell us what it is, but notice how it bends towards the normal in medium Y, and it would only do that if that's your normal line for this intersection, if N is bigger than 1.5, meaning it slows down if it bends towards the normal if it slows down. So it's got to be slowest in medium Y. Okay. The sine of theta x is, okay, air, lucite. So air, n equals 1. Lucite, n equals 1.5. Whoops, I got that down already. So let's do this as a Snell's law. Notice how it's asking not for theta x, but it says the sine of theta x. And theta x is the refracted angle after it first enters. So it would be 1 sine 30, which covers the air, 1 sine 30, equals 1.5 sine theta x. That's the x. Okay. So having said that, sine theta x is then for sine 30, which is a half over 1.5. So 0.5 divided by 1.5 gets you 0.33. Third. There we go. Boom. Pay attention. Sometimes they'll try to make it easier. Like, what's the sine of theta x? When you actually try to solve for theta x. A monochromatic ray of light, again that number, traveling through air is incident on a medium at an angle of 45 degrees. The angle of refraction is medium A could be. Okay, so let's see. It's traveling in air. So 1 is the angle of the index of refraction at an angle of 45 degrees. It's 1 sine 45 equals n sine 29. So n is equal to, see, sine 45 over sine 29. Sine 45 divided by sine 29, which is equal to 1.45. So what has an index of refraction of 1.45? It's probably going to be quartz, 1.46. Does this round up to 1.46? It does. It rounds up to 1.46. Fused quartz. Fused quartz right there. 1.46. I'll change that. Okay. Light passing through a medium into air. Notice how it bends away from the normal as it passes into air. What's the index of refraction of medium X? Okay. N sine 30. That's the incident angle in ray equals 1.0 sine 60. So n is equal to the sine of 60 over the sine of 30 times 1 sine 60 divided by sine 30. And you might even be able to solve this if you know your trig without using a calculator. 1.73. There we go. It'd be bad if you got A. You can pretty much just cross that out. And D you could just cross out because those are both less than 1 and you're not going to get an index of refraction less than 1. Okay. A ray passes from glass. Air into glass. Air into glass. Dotted line tells you the normal. Air, glass. What relationship represents the index of refraction of glass? So it should be 1 sine B. Lots of interesting, we have A's and B's there, right? Equals N, which is the index of refraction of glass, sine D. So let's simplify, divide both sides by sine D. Boom, and you get N equals 1 times sine B over sine D. Sine B over sine D is equal to answer D. A ray of light, again this number, is incident on water, air, as shown in the diagram below. Calculate the index of refraction, calculate the speed of light. Should be pretty easy. We know that it is going from water to air, so 1.33, which is the index of refraction of water, 1.33, is times the sine of 40 equals 1.0 sine theta. So 1.33 times the sine of 40 equals 0.85. So sine theta is 0.85, which means theta is the inverse sine of 0.85. Inverse sine 58.7 degrees. Calculate the speed of light while in the water. Well, N equals C over V. So we want to find the speed of light while in water. That's V. So V is equal to C over N. C is 3 times 10 to the 8th meters per second. N is 1.33. Notice equation, substitution with units, meters per second, and there are no units for index of refraction, which you'll get right here. Nothing, no units, water 1.33. So 3 divided by 1.33 is 2.25 or 2.26 if we want to round up, times 10 to the 8th meters per second. Units are on the answer too, 2.26. Okay. There's a transverse wave. On the wave diagram, draw a transverse wave that would produce complete destructive interference when superimposed. So if this has an amplitude of 2 boxes and a wavelength of 2 big boxes, the other one should have an amplitude of 2 boxes and a wavelength of 2 boxes this way. But if this is positive amplitude, this one should have negative amplitude. So the first one is going to go down 2 and up like that. The next one's going to go up 2 and down like that. This is positive, so let's go down. And here we go, destructive interference. If you had constructive, it would be the same as the very top one. A transverse wave with an amplitude of 0.2 meters. Oh my gosh, it even tells you what the amplitude is. And a wavelength of 3 meters, let's see. Does that make sense? 1, 3. 1.5, 3. Good. Travels to the right. They're really nice that they even told you that. You did not need to do that. Travels to the right with a speed of 4 meters a second. Calculate the period of the wave. There's different ways to do it, but let's just find the frequency. So velocity is frequency times wavelength. Frequency is velocity over wavelength, which is 4 meters per second over the wavelength of 3 meters. Should get you 1.33 hertz, which is 4/3, by the way. So period is 1 over the frequency. Look at your reference table if you're not sure of these equations. 1 over 1.33 hertz was 4/3, so the answer should be 3/4, so it should be 0.75 seconds. 1 divided by 1.33 equals 0.75. That's 4/3, so that's got to be 3/4. Array, more of the same number, traveling in air, incident, blah, blah, blah. Calculate the angle. I think this time we're probably going to have to draw it, though. So we get air, 1.0 sine 40. 1.0, water, 1.33. We've looked that up. Equals 1.33 sine theta. So theta is going to be the inverse sine of sine 40 over 1.33. Sine of 40 divided by 1.33 is 0.48. Take the inverse sine of that. Gets us 28.9 degrees. There we go. Now let's use a protractor and draw the ray. Okay, so we're looking for basically 30 degrees. Not 0, there's different ways to do it. If you want to hold your protractor like this, you can. And you just go over 10, 20, 30. That's 30 degrees. Technically 29 degrees, right? Let's go over right there. I'm going to go over just a tiny bit. Go like this and just count out 10, 20, 30, as long as you know whatever you're doing. Draw this, and that to that. Put an arrowhead on it and label it refracted ray. Now it says use a protractor and a straight edge and draw the reflected ray. Well, the reflected ray is going to reflect off the water and back into the air. And this has an angle of 40 degrees, then the reflected ray should have an angle of 40 degrees also. By the way, I never even checked to see if this is 40. It should be 10, 20, 30, 40. Good. So the reflected ray is going to have an angle of 10, 20, 30, 40. No reason not to use a ruler for this. That's going out that way. Draw an arrowhead on it, and we can do reflected ray. There we go. Now, note, air on water, you're always going to have a reflected ray and a refracted ray. If you did it the other way around, if you went from water into air, you were always going to have a reflected ray. Sometimes you may have a refracted ray, sometimes you will not, because you're going to have at some point total internal reflection. So if you slow down, you're always going to have a refraction and a reflection. But if you speed up, like you go from water into air, then you're going to have a reflection, but not always a refraction. What color of visible light has the lowest intensity? Lowest intensity is going to be out here. So that is the highest frequency. And we look here, and we look frequency here. Frequency gets higher as you go to the left, so that's probably violet. That's the highest frequency. It's suggested that fire trucks be painted yellow-green instead of red. Why? Well, perhaps that's because the peak intensity is yellow-green. so they could have the highest intensity. And this is because this might be white light, but white light is made up of many different colors of light, but they're not all evenly balanced. Sometimes there's obviously a lot more yellow-green than there is violet light. But when they combine, they form white. And you can make them into a rainbow, but as you can see, if you make them into a rainbow, some parts of the rainbow might be brighter than others because they have a higher intensity. Okay. Diagram. Light ray strikes the boundary. Using a protractor and a straight edge, determine the angle of incidence and draw the reflected ray on the diagram. This one does not do a normal line, which is a little bit trickier. So let's do our normal line. I'm going to find where it intersects. There we go. I'm going to do the normal like this. Normal. There we go. Dotted line. Let's measure this angle from the normal. 10, 20, 30, 40, 50, 60 degrees. So that's 60 degrees. Theta I equals 60 degrees. So that means theta R is going to be 60 degrees also. So we go 10, 20, 30, 40, 50, 60. Perfect. What is the amplitude of wave C? Let's make sure we get the wave. That's the dotted wave. Notice the whole thing goes 4. So it means each box is 1 meter. So from the middle to the top, that's one box, 1 meter. 1 meter. What's the period of wave A? Well, this is a bit odd. Let's think about this. Let's find the wavelength of A. Now I can figure out based on the scale, but 1 wave, 2 waves, 3 waves, 4 waves. So 4 times the wavelength is 12 meters. So the wavelength is 12 over 4, which is 3 meters. So if the wavelength is 3 meters, I feel like we're missing some information. Oh, it goes 12 meters in 2 seconds. Okay, there we go. I'm going to do these in slightly different order. Because they're all going at the same speed. The speed of wave B is, well, let's see. In this case, you could do frequency times wavelength, right? But we can also do distance divided by time. So it goes 12 meters in 2 seconds. That means it's got a speed of 6 meters per second. However, let's find the period now. Period is 1 over the frequency, so frequency is going to be velocity over wavelength, which is going to be, in this case, 6 meters per second over the wavelength of 3 meters, which we found there. So the frequency is 2 times 1 over seconds, or 2 hertz. So that the period is 1 over the frequency. It's 1 over 2 hertz, which is a half second, 1/2. That's a second. Good. A ray of light passes from air into a block of transparent material, as shown in the diagram below. Measure the angles. I'm going to pause for a second before I finish this. I'm back. Ms. Miller was just here. She want to say hi? There we go. Measure the angle, incidence, and refraction. Lots of crap up here. We don't need to read that. Pictures are always nice. To the nearest degree. Usually the Regents exam will give you about 2 degrees. Now, it is a bit challenging when the arrows are that short. You can make them longer. Let's just, because it doesn't ask us to draw on here. I think I can do that okay. Measuring it from the normal, so 10, 20, 30, 40. 3, it's hard to read exactly, about 44 degrees. So we're going to call that 44 degrees is my angle of incidence. And my angle of refraction is, let's see, 10, 20, 25 degrees. So theta I, well, let's call them theta 1 and theta 2, because that's what the reference table does. Incidence, refraction. Okay. So incidence is 44, refraction is 25. Calculate the absolute index of refraction of the material X. So 44 degrees goes with air, which has an index of refraction of 1. 1.0 sine 44. Put the degree symbol in because it shows all work. And that is equal to the index of refraction of the material, N, times the sine of 25 degrees. Now, right now, I am looking at half credit, even if I solve this correctly, because I did not put down the equation and substitution with units. So, N1 sine theta 1 equals N2 sine theta 2. Let's call that N2 just for consistency's sake. So now I can solve it, and I can say N2 equals sine 44 over sine 25. I've already done the substitution with units. I don't need to put units in here, so I do not need the degree symbols in there if I don't want to. Sine 44 divided by, sine 44 divided by sine, ooh, look at that, 25. I have a mistake in here already that I made. Sine 44, let's close the parentheses. If you don't close them, you're going to make mistakes. Divided by sine 25, close parentheses. I'm going to put the degree symbols in there, by the way. 1.64. No units for that, because it's a ratio. Good. The refracted ray, oh, crikey. It asked me to draw the reflected ray. That's fine. I haven't gotten in the way of that. Using a protractor and a straight edge. So if that's 44 degrees, the reflected ray, let's see which one it wants. Because you're going to have a reflected ray here, and you're going to have a reflected ray there. The refracted ray is reflected from the material X air boundary at point P. Use a protractor and a straight edge. Draw the reflected ray from point P. So this is the ray I want to draw. So if that is 25, then that's going to be 25. We can do a normal line there too. Technically, I should do it at... Let's do that dotted line thing. Dink, 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 dink. Okay. So that, if that's 25, that should be 25, which means this angle right here, and I could measure it just to be clear, but that should be 65 degrees, right? 10, 20, 30, 40, 50, 55. That's right. That is 25. What am I doing right then? 10, 25, 10, 20, 30, 40, 50. Oh, I'm looking at this ray. I'm like, what am I doing wrong? I need to look at this ray and it's not extended. But that should be 55 degrees. 10, 20, 30, 40, 50, 65 degrees. 65, good. So the reflected ray should also have an angle of 65 degrees, which is 10, 20, 30, 40, 50, 65. So it should go from there to there. Put an arrow on that. And you can label that reflected ray. Which means that should also be 25. If that's 25, that should be 25. They are symmetrical, but technically the angle, because it's measured from the normal line for this particular interaction is here, is going to be 65 degrees. Sketch 4 wavefronts after they've passed through the barrier. Wow, this is easy. This is diffraction. Boom. There we go. You can probably do a prettier job than I did. Periodic wave. Draw at least one full cycle of this periodic wave with an amplitude of 0.2 meters and a wavelength of 3 meters. Let's see, 1, 2, 3, that's one full wave. Amplitude is 0.2 meters. That means it needs to go all the way to the top and all the way to the bottom. Now at halfway through the wave, if I'm going to start here. That means it's going to go up and down like that. So that's going to be a 0 point, which means halfway is going to be a max, and halfway is going to be a min. So I'm going to go. There we go. Amplitude 0.2, wavelength 3 meters. An electromagnetic wave, it's radar, interestingly enough, is emitted by a weather station and reflected by a nearby thunderstorm. It's moving towards the weather station. Using one or more complete sentences, explain how the Doppler effect could be used to determine the direction which the storm is moving. That's interesting. They ask for complete sentences. Okay, I gotta use a complete sentence. The Doppler effect could be used to determine the direction which the storm is moving. So the Doppler effect tells you how the frequency of a wave changes. So let's just say if the storm was moving towards the station, let's see, frequency of the wave would be higher, right? Frequency of the reflected wave would be higher if it was moving away from the station. I want to speak more quickly. The frequency would be lower. Higher frequency, lower frequency. Except these are E&M waves, not electromagnetic waves. Light, basically, not sound. Okay. Two waves pass through the same medium at the same time. Name a wave characteristic that is the same for both of them. I look at them, they're not the same length, clearly. They're not the same length. There's probably not going to be, they're through the same medium the same time. Probably not going to be the same frequency either. You don't know the speed. Odds are they probably are the same speed, but more than that, like let's look at the amplitude. They go up 2 boxes, down 2 boxes. So they have the same amplitude. They may not have the same speed. They may have the same speed. You don't know if they're the same kind of wave. It doesn't tell you. But if they're the same kind of wave, odds are they probably do have the same speed. Energy, probably not. You know, maybe. It depends. Ocean waves would have the same amplitude, so they have the same energy. Light waves, the energy depends on the frequency, and since they don't have the same frequency, they do not have the same energy if they are electromagnetic waves. What's a characteristic that's different? Let's just go wavelength. Different length. Those are the things that are really obvious to me. Again, frequency is probably different. Velocity is probably the same. But those are the two that we know that are definitely the same and different. Sketch the wave pattern when the two waves interfere. That's kind of annoying. This is not easy to do. Okay. Let's draw a line just to make this a little easier for me. Because at this point here, 2 boxes in, I mean, at the beginning, they're a box in, they're both 0, right? The next box over, the total amplitude is a little more than 3. The next one, it is back down to 2. 2 plus 0 is 2. Now it is -2 plus about 1.5, so -0.5. Here it's 0. Next box over, it's up to and a -0.5, so it's a -1.5, so it's up about 0.5. And here it's down 2, plus 0 is down 2. Then here it's down 2 plus another 1.5. And here it's at 0. What the hell? Why do they ask me to do a wave pattern for interference like this? Something like this, I don't know. Something like that. It's clearly not, it's not a standing wave because they don't have the same frequency, so you're not going to get a standing wave. Weird question. I hope they never ask one like that again. But you can figure it out. Okay. What is the measure of the angle of refraction? See, this is nice and long. This is how I like it. The angle of refraction. This is incoming, that's outgoing. So angle of incidence is 30. Angle of refraction is 10, 20, 30, 40, 50 degrees. Nice and easy, 50 degrees. If you calculate it, which you could, show your work. Oh, you want me to calculate it? Because this is lucite, and that is air, and it is bending away from the normal. So let's look at lucite. You could do, if you use a calculation, show all equations with paper substitutions. Let's do it this way too. Lucite has 1.50. So 1.5 times the sine of 30 degrees equals 1.0 for air is the index fraction, sine theta. So theta is the inverse sine of 1.5 sine 30. Now 1.5 times the sine 30 is 1.5 times a half, so it should be 0.75. So the inverse sine of 0.75 is theta is equal to 48.6 degrees. So our measurement of 50 was pretty darn close to 46.8, but this time I actually calculated it. I did not. It says show all equations. N1 sine theta 1 equals N2 sine theta 2. Forgot the equation, I'm putting that in there. Determine the speed of light and lucite. I'm going to do that here. N equals C over V. V equals C over N, which is equal to 3 times 10 to the 8th meters per second over 1.5. So that's 2 times 10 to the 8th meters per second. Determine the critical angle. Okay, so not on the reference table, but at the critical angle, this was going to be 90 degrees. So it's going to be coming in, and instead of going there, it's going to be going there. So you're going to, and we don't know what that angle is. Let's just call that theta crit. Coming in, boom, bouncing off here. If you remember, we did this in class using the water lens. So our water lens was placed like this. It's going off at the critical angle. So in that case, just like we did there, in lucite, it's going to be 1.5. It says show N1 sine theta 1 equals N2 sine theta 2. So 1.5 is lucite's N times the sine of theta crit equals N2, it's air, 1.0, times the sine of theta 2, which is going to be 90 degrees, measured from the normal. So theta C is going to equal the inverse sine of, well, let's do sine theta C. Sine theta C is equal to what? 1 times sine 90, which is just, sine 90 is 1, so it's just 1 over 1.5. 1 divided by 1.5. Which is 0.66666. So theta C is the inverse sine of that, which is equal to 41.8 degrees. So that's the critical angle right there. And that does it. Thank you very much.